So I implore you to stay with me and ask lots of questions and don't all slowly fade away on me. Fortunately, we have saved the most technical talk for the last one of the workshop, which is fantastic. Which I'm sure you'll all enjoy. But this really picks off from where we were yesterday. So luckily, lots of the groundwork has been set. And essentially, this is leading off some work that I did with a fourth year student, a master's student, and my fantastic student Tang Bui and Kung, who's also a fantastic postdoc. And we set this student the task of looking at what is an almost uncited paper that was looking at applying a method called expectation propagation that you've looked at, that you've heard about, to sparse GPs. And he spent a long time sort of coding it up and battling away with it. And then he discovered something really interesting that has been completely overlooked, or largely overlooked by the field that's working on Gaussian processes. And I'm going to tell you the story about what that thing is that has been overlooked and why I think it's really important in this talk. Okay, so here's the motivation again. It's the same motivation as we had yesterday. We'll start with just talking about Gaussian process regression, but everything I will talk about also applies to classification and more complicated models, as was sort of pointed out in Alan's talk this morning, which was fantastic. So we have some data, black crosses, outputs are y's, if you remember, and inputs are x, and we want to make predictions at some unseen input. And ideally, we'd like to fit a beautiful Gaussian process through it, carry out inference and learning, and get lovely error bars that indicate how uncertain we are in the region of interest and a nice estimate for the mean. But typically, this is intractable. It's intractable for two reasons. Firstly, it's computationally intractable. So we might just have too many data points to invert these matrices and compute Cholesky decompositions. But it's also often analytically intractable if we have things like these non-Gaussian likelihoods like we do in classification. And ideally, we'd like to finesse both of those, deal with both of those sources of intractability at inference time in one go. Okay, that's going to be the goal here. We're going to deal with them both together in a really smart and clever way. Great. Okay, so let's go back to this history of Gaussian process approximations that we flagged up yesterday, and I'll explain a little bit about how what we're going to do today fits into that history. So here are our approximate generative models, where we write down a model that we believe in, and then we write down a different model that we don't believe in, but which is computationally tractable, and then do learning and inference in that. And there are these methods which use pseudo data to get those computational savings, and FITSI is one of the methods that I talked about that does that. That's sort of the archetypal example, and these other sort of derivative models that are related to FITSI, which I'll touch on today. And there's this fantastic review by Joaquin and Carl about that. And then we had this other philosophy, which the sort of the variational free energy method we talked about yesterday took, where it said, keep the model sacrosanct, don't touch it. At inference time, go in and make all the approximations. And I sort of argued why that was sensible. And what we're going to do today is, and this is sort of the magic, is to show you that FITSI, and indeed these other cases, can actually be interpreted as expectation propagation. So under the hood, this thing that we thought was doing approximate generative modeling on the left-hand side here can alternatively be reinterpreted as running EP as expectation propagation, given some particular inferential assumptions. So it has this sort of dual view. This is where I was getting annoyed at my master's student, because he implemented EP and he'd run it, and the traces that he was coming out of it were looking exactly the same as FITSI. I'm saying, no, there must be a bug in your code, because we're supposed to be comparing to FITSI, and it looks just the same as FITSI. But no, that was because EP is FITSI, or FITSI is EP, which is kind of interesting. So this is laid out in this paper, and what's really nice about this is we can actually subsume all of these methods into one unifying framework using a generalization of EP called power EP, which is really easy to understand once you've got EP, which is hard to understand in the first place, but we'll get to that. Okay, so here we go. I'm going to sort of pick up where Alan left off and maybe provide a bit more context about what expectation propagation is. It's one of the most generally sort of poorly explained pieces of approximate inference in the literature, but I don't think it's actually too hard to get to grips with if you look at things the right way. So we'll attempt to give sort of a clear introduction to EP here and hopefully point out some misnomers in the literature. It starts, though, with a little bit of a twist, and this is sort of something which perhaps isn't stressed in the literature enough, is one way of thinking about approximate inference is not as approximating the posterior. I like to think about it as approximating the joint distribution directly. So here our joint distribution is over function values, the latent function values f. And again, this f here contains all the uncountably infinite values on my function here and my data, and it's conditioned on the inputs x and the parameters theta. And I'm going to call this p star of f. That's this thing here, p star of f. P star, anything with a star, indicates it's not a normalized density. Okay, so this is not a normalized density over f, because this is the joint distribution of f and y. If I renormalized it, if I divide it by p of y given x and theta, that would give me the posterior density, and that would be normalized. But at the moment it's not normalized, so it's got a star in it. And we know how to write down this joint density for regression and classification. We just take our Gaussian process prior, and we're going to make the assumption that the data are IID given the inputs associated with that data point and the infinite dimensional function value and the hyperparameters theta. Okay, and this in general is going to be something which is intractable. It might be some nasty classification likelihood, so it's got a red line underneath it to indicate that it's nasty and horrible. Now, there's an alternative way of writing the joint distribution, of course. We used this yesterday when we talked about the variational free energy. And that's to decompose it using the product rule of probabilities in terms of p of y given x and theta times p of f given y, x and theta. So this is just using the product rule, p of a comma b equals p of a, p of b given a. Yeah? Make sense? So I've just split it up like this. It's a trivial identity. This first thing is the marginal likelihood. This is the thing we need for learning, whether we're going to do maximum likelihood learning or maybe something more Bayesian. And this is the posterior. So this is the thing which we said, if we renormalize p star by this thing in here, then we'd get the posterior. Great. Okay. And the approach we're going to take in EP is to approximate this joint distribution. So it's the distribution of the function values with the data that we've observed. So the data are going to be clamped to their observed values, and we're going to approximate that with q star of f. Okay? Okay, let me just explain why we're going to do that in just a second. So hold off for 30 seconds and I'll explain why q star approximating p star is a sensible thing to do. What I want to draw your attention to before we talk about that is q star is going to have exactly the same form as the joint distribution over here. It's going to have the prior, and the exact prior that I had over here. So I'm going to borrow that and use that in my q distribution. And then I'm going to multiply it by a product of t sub n's of f. And in a minute, what we're going to do is going to construct an algorithm for refining each one of these t's so that it approximates each one of these likelihood terms in here. Okay? That's going to be the goal. We're going to refine a t n so it approximates a p of yn given f and xn by an algorithm. But these are going to have a nice simple form. Okay? These things are going to be a Gaussian functional form in here. And this is a Gaussian prior, and a Gaussian times a Gaussian will then give us a Gaussian Q distribution. So Q star is going to be something which is going to be analytically tractable. We could integrate it, we can compute its moments, whatever we want to do, because it's just a plain old Gaussian. And what's nice is, of course, this could be decomposed in terms of a normalized bit, Q of f. If I take my unnormalized Gaussian here and just integrate it to figure out what its integral is, call that z, and then multiply that by now a normalized bit. And what's nice here is this normalization constant in here will approximate the marginal likelihood over here, and this normalized bit in here will approximate the posterior in here. So for free, if you view approximate inference as approximating the joint distribution with the data fixed, approximating p star, you will refine an estimate to the marginal likelihood and an estimate to the posterior together in one go. Okay? And it turns out that actually there's a way of looking at traditional variational inference which operates on approximating these joint distributions too. And it gives you the marginal likelihood, the elbow is ZEP, and the Q distribution in variational methods is this one. Laplace's method similarly is usually set up as an approximation to the joint distribution, and it also gives you an estimate for the marginalizing constant and an estimate for the posterior. And importance sampling is another example where it again gives you an approximation to the unnormalized joint in terms of a normalization estimate and a posterior estimate. So many classical approximate inference methods can really be thought of as approximating the joint distribution. All right, everyone happy? Have I lost anyone so far? Okay, this is just the form of the distribution to start with. Let's talk a little bit more about this. So we want to do sparse approximation. So at some point, these u's have got to turn up rather than our function values, right? And here's the point at which the u's make an entrance. The t sub n's in here, the bits which are approximating each one of our likelihood terms, we're going to let them be Gaussian, like I said before, but we're not going to let them depend on the entire infinite dimensional function. We're just going to let these depend on a small subset of u pseudo points. So m pseudo points with associated inputs on the function are going to enter into each one of these tn's, not an arbitrary number of points on the function. Okay, so in other words, the true likelihood over here just depends on the function value at the particular input xn, and we're going to approximate that with an approximate likelihood function over here, which depends on a whole vector of function values at predefined m input points. Okay, and it's not going to be the case in general that the actual function value here is contained in this set of pseudo points. Yep. N is the number of original data points in here, and m is going to be the dimensionality of u, the pseudo points. Okay. Great. So one way you can think about this, just as a notational thing for later, is I've partitioned the infinite dimensional function into u, the set of pseudo data points, and f not u, all of the rest of the function. Okay, so we partitioned it to 2 bits. Okay, great. What shall I talk about next? This can be hard to get your head around, but let me talk through this. This confuses some people, so ask me a question at this point if things are not clear. Let's do some maths in our head. Let's collect together this product of approximate likelihood functions here. That's a product of these multivariate Gaussians in U. And we'll collect all those together. A product of multivariate Gaussians in U will give us another multivariate Gaussian in U up here. Yeah? And I can think of that multivariate Gaussian as being a pseudo likelihood. I can think of it of these things when they're collecting together, taking that multivariate Gaussian in U and rewriting it as P of y tilde, where y tilde are some pseudo observations and a covariance matrix, and these will depend on the mu n's and the sigma n's down here, and our u's down here. Okay.
Quick question, Rich.
Yep.
Aesthetically, because of this fact, I always prefer to think of the t as a distribution over mu given u.
You could do it that way. Yes, you could flip.
And it doesn't really change anything.
No, it does.
Much, does it? But it gives you at least the thing at the top is the same right way around condition.
Yeah, that's true. The thing at the top would then collect together all those mu's, so it's not one-to-one, but I can see that makes, maybe that's a better way of thinking about it. So Neil's saying the functional form of Tn of f here is just the same if I flip u and mu n in here. Like if you think about, you can always flip the mean and the variable in the definition of a Gaussian. It will give you the same functional form as you come out of it. So here we've been thinking of u as the distribution being over u, but I could have alternatively thought about it as being the distribution being over the mu's, and I could think of the mu's a bit like these pseudo observations at the top. And because what we're going to play the game in a minute, the EP algorithm is going to move around these pseudo observations, these fake data points, and it's going to move around this covariance matrix in here in such a way that when we do exact inference on this model at the top, where we form the true posterior of this approximate model, it's close to the true posterior over here. Okay, so in a way you can think about both the variational algorithm and the EP algorithm as moving around these pseudo input locations, the input locations of the u's, and the corresponding observations at each point, the y tildes, and altering the noise error bars in such a way that when we do exact inference on this fake data set over here, we're as close as possible to the true posterior. So it's like setting up a toy regression problem where you get to fiddle around with your data and you get to fiddle around with your Gaussian noise model such that when you do exact inference on that toy data set that you've created, it's going to be like your non-Gaussian complicated posterior with lots of data points on the left. Have I confused people here? Possibly. Questions? Nope. That interpretation is not essential for understanding the rest of the talk. Understanding this functional form is.
Just to be clear, you're setting up now, you're just setting it up so that you can then populate it?
In a minute.
Yeah.
I have not given you an algorithm so far. This is all about the form of the approximate posterior. Yeah, this is just about the shape of the approximation, the particular assumptions we're building into the approximation. Yep. Great. Okay. EP. This is the hard bit. All right, I'm going to give you, because most of you haven't met EP. Who knew about EP before the workshop? All right, so I definitely need to do a bit of work here. Okay, so let me just try and give you one justification, a justification I quite like for the EP algorithm. And I will do that by starting off with an idealized algorithm that does not work, as in it's not going to save us anything on computation, but it will at least motivate the EP algorithm. So remember, our goal is to refine these TNs. Okay, so here's an idea for how we might go about refining those TNs. Let's take the KL divergence between P star of F, our true joint distribution, with the data fixed at the observed values, and P star of F. I'm going to remove one of the data points from that joint distribution. So I'm going to remove the nth data point. Can everyone see this? Is this big enough and black enough? Guys around the corner might struggle. Happy? And I'm going to add in Tn. Let me write this as F to the minute, but really it just depends on you. Okay, and we're going to minimize this over Tn of F. And you can see, so what we've done, we've removed the effect of one data point from our joint distribution, and we've put in the approximating factor. And if we minimize this KL, that should force this Tn to be as close to this thing as possible so that we're equal to P star of F on the left-hand side. And then we could just make one sweep through all of our n data points, carrying out this minimization for each one of our approximate likelihood factors, collect them all up together, and compute our Q distribution. Okay, that might be a sensible thing to do. It's unfortunately not going to work because this thing on the left-hand side here involves our true joint distribution. So analytically, this is still just as complicated as operating on the posterior to start with. So it's unfortunately doomed to failure. But what we can do is we can rewrite things slightly. So let me rewrite this side as the joint distribution divided by, you'll see why this is useful in a minute, divided by the nth data point likelihood times by the nth data point's likelihood. And on the right-hand side, notice we've got a similar form. We've got P star of F divided by P yn of F and xn and theta Tn of F. So this is another way of writing that KL divergence minimization. And the idea in EP is to say, let's approximate this bit, which appears on both sides. It's the posterior with one of the data points removed. You should think back to Aki's talk. Aki talked about this a lot. You'd compute a posterior and you'd remove a data point. This is exactly the same thing that was showing up in his talk. It's intractable here, so what we're going to do is we're going to approximate it using our Q distribution. We're going to bootstrap. So we're going to substitute in here instead Q star of F, and then we have to approximate the leave one outness here, so we're going to divide it by Tn of F. So rather than using the real true leave one out posterior, we use the approximate leave one out posterior. let's just write that up. And the same thing on the left-hand side. And this is going to be the old value of t here. Okay, so we take our current approximation to the joint distribution, we remove out our approximate likelihood, and on the left-hand side we substitute in our true likelihood for that data point. And on the right-hand side we do exactly the same thing, we remove our current approximation to the likelihood factor, and we substitute in our new updated one, and then we're going to optimize this with respect to Tn, the new Tn in here. And you can see what that's going to try and do is approximate this guy, approximate this likelihood in the context of the approximation to the prior and the other data points. So rather than approximating this thing directly without regard to what the effect of the other data points, which would be a bit silly because then we haven't sort of taken into account, well, how does this particular data point affect the posterior? This approximates this in the context of what we think is going on in the rest of the posterior. So it will only concentrate on aspects of this likelihood which are affecting the posterior. That makes sense, or the joint distribution equivalently. Everyone happy? So we're doing argmin of this over Tn of theta. Notice up here we could got away with one pass through because the Tn's don't interact with one another. We could have just gone through each data point, done it once, put them all back together and got Q and we'd be happy. Through this method, the update for Tn will depend on all of the other T primes that are in Q star. So now the updates are all coupled, and we'll have to iterate this till convergence. Okay, so it'll take some time to settle down. And this thing is called EP. That's the EP algorithm at the bottom. Sorry? People don't know. Yeah, empirically it often does. And in the Gaussian case it's guaranteed, but in general we don't have convergence proofs for EP. So it might explode. All right, are people happy at this point, roughly speaking? Yep, question, good.
When you say iterate equal convergence, you're iterating like for a specific Tn, but then you also have to do it for all the data points, right?
So this will typically, well, this will often be a closed form update. So this optimization will have an analytic solution, and then you move to the next data point, update that, go all the way through, go back to the start, and so on and so forth. Yep.
Yeah, I just wasn't sure how you move through the data points, if it's random or if you go.
It can be scheduling's an awkward question, but yeah, one way we just through the data point back to the start, through the data point back to the start. You could do some more smart things, and people haven't done enough research on that, I think, but that's what we're imagining here. Any more questions on this? So we're going to recapitulate this on this next slide, actually. So here is the EP algorithm. A little bit more notation here. I'm going to call this thing Q not N, because it's the Q with a data point, an effective likelihood removed. So we're going to remove one of our pseudo observation likelihoods. We're going to put back in one of our real observation likelihoods. That's to get this left-hand side here. This is called the tilted distribution. This is a sort of statistical physics lingo because it's tilted our approximate posterior towards the true posterior by including one actual data point rather than our approximation. So you probably don't need to know this terminology, but that's called the tilted distribution in the literature. And then we're going to carry out this projection. So we're going to carry out argmin of KL between the tilted distribution, that's just the thing down there on the left, to Q star, and we'll be home and dry. Two things to note here is it's equivalent to update Q star and then by division recover the Tn. So here I wrote down the optimizations with respect to Tn. I could have equivalently written it down as an optimization for Q star, and then you divide out the prior and the previous Tn's in order to figure out what the new Tn is. So you can, sometimes you'll see people write it one way and sometimes you'll see people write it the other, and here's how we get that division back. We take Q star and we divide it by what's called the cavity distribution in here to get back Tn. And that updates our pseudo observation likelihood, and then we're going to go back through and do the whole loop again. Okay, so this is exactly the same as Alan went through this morning. basically. Sort of recapitulated his algorithm in a slightly different case that now our t's just depend on the u's, not on the whole vector of f's, like he did in his case. Everyone happy so far? Anyone want to go home now? Probably yes, everyone. Great. Okay. One other wrinkle is this. This is something also that confused me a lot looking at EP literature. These KLs in here, nobody asked the question over here. This is a KL between two unnormalized distributions or two joint distributions. The KL that I saw before was for normalized things. What's going on here? Well, it turns out there's a trivial generalization for what you know is your KL divergence that operates on unnormalized densities rather than normalized densities. It just has a correction term after the standard KL bit. And it's just as tractable as the normal KL in exactly the same ways. So don't worry about it too much. Great. So it turns out that there are a couple of things you can prove about this KL optimization here. The first thing that you can show is that this will have a minimum, this KL minimization will have a minimum when the moments are matched at the pseudo inputs. So rather than having to match moments everywhere, so the KL P to Q, the solution of a KL Q to P minimization will typically match the moments of P in Q. So the Gaussian here will match the moments of P. That's a general result across sort of exponential families in general, where Q is the exponential family distribution and the KL is from P to Q. In this particular case, where we have these U's, it turns out you just need to match the moments at the M pseudo input locations. So compute the mean and the variance of this distribution at each one of the pseudo inputs, and the cross covariance, and then update Q star of F to accordingly to match those moments. So that Gaussian has that mean and it has those variances. It turns out in the regression case, we're going to match moments everywhere. The reason why this is important, that the moments need to be matched at the pseudo inputs, is because that reduces the computational cost down to order nm squared here. This is the origin of moving from n cubed complexity to nm squared complexity. Great. And it's also the case that these TNs are low rank as well. So they end up having a rank 1 update that looks like this in any case when you've got any pointwise likelihood here. And this low rank structure, again, is tied into this order nm squared reduction in computational complexity. Great. OK, people roughly with it so far? Questions? Great. OK, so I'm not going to go through this proof, but here's what essentially my student found. He ran this algorithm over and over and over again. And this is a proof of what happens when you do that. I'm not going to talk you through it. But bingo, you get Fitzy out of it. So this converges. It converges every time. And the fixed point is exactly the same as the Fitzy approximation that we talked about last time from the perspective of generative modeling. So we then went back through to the literature and thought that somebody must have known about this. And sure enough, Manfred Opper and Lehil Sato knew about this in 2002 in their paper. This is one of the foundational papers in sparse GP literature. It was focused on online inference in Gaussian processes. It's got 500 citations, but somehow people haven't made this connection between, there are some threads in the literature, but in general, people didn't know that this was Fitzy in here. They knew about it 15 years ago. And Manfred's papers are often quite hard to understand. He's brilliant, but they're quite hard to understand. And you know, we lost that sort of nugget, but we've rediscovered it now. Tom Minker knew about it in 2010. This is the only other citation we could find that acknowledged that this relationship holds. You can think of this as EP. Great. OK. So some of the nice things that come up from this is, well, yesterday we ended with this sort of philosophical quandary about Fitzy. We said, if we're thinking about it as approximate generative modeling, we're not allowed to increase the number of pseudo points as we see more data, really, because that's changing our assumptions about the data. Whereas this interpretation is saying, no, that's just fine, because it's EP, it's approximate inference, and we can run more sophisticated, computationally more rich models at inference time if if we see more data, we can rerun inference multiple times with different degrees of complexity. That doesn't change our modeling assumptions, it just changes the amount of computational resources that we want to donate to posterior approximation. It also tells us that the FITSI likelihood can be bigger than the GP likelihood. So there's an easy thought experiment to show that this is the case. So imagine taking the FITSI approximation yesterday and having as many pseudo points as data points, and putting each one of those pseudo points at the data input locations. It turns out that will give you exactly the correct marginal likelihood for the model. It will have the same marginal likelihood as the true model. But now we can optimize the pseudo input locations. And in general, when you'll do that, you'll get bigger likelihoods because you're optimizing them, and they'll move away from the data, and often they clump together and sit on top of each other, and some of them wing off to infinity, but they'll give you a bigger marginal likelihood estimate than the true marginal likelihood. And so you can sort of interpret that as EP overestimating the marginal likelihood, and that's something we know that EP can do. It's not guaranteed to give an underestimate like the variational free energy method. Yep?
I have a question is that you make a link between EP and FITSI, and we know EP might not converge. So does that link only mean that the fixed point of EP actually match with the solution of FITSI, but it does not guarantee that EP converged solution will be equal to FITSI?
Yeah, we don't have the convergence proof, but I suspect for this Gaussian case it always converges. But we don't have a convergence proof for that. It's a good point. Yeah, so we know that if you took the FITSI solution and plugged it into EP, that would be a valid fixed point of EP. And then we have empirical evidence that it always converges to FITSI, but we haven't got a concrete proof yet. Yep.
So, consequence of this overestimating the likelihood is that then that it underfits and overestimates variance?
It's hard to say what the consequences are. I don't know whether maybe Neil has some, or other people have used FITSI, Aki. What typically it does, I think it's hard to say what the pathology is. I mean, often it clumps together the pseudo points, and then it will estimate length scales which are too large, which is sort of underfitting. Is there a consequence on parameter estimation of the overestimation of the marginal likelihood that FITSI can provide? I think Aki's about to.
So it's because it's matching the marginal variances. So those are
They're correct.
correct.
Yes.
But then the posterior coverage matrix is not correct.
Correct. Yeah. So the noise will have to be smaller. Yes.
Why you get slightly different result, and if you would be able to optimize the KM divergence jointly.
Yes. So in that context, the noise would be underestimated.
So my intuition to that is because you can also look at it as a weird heteroscedastic noise model.
Mm-hmm.
And optimizing over heteroscedastic noise is not normally a good idea unless you've got strong constraints on it.
Yes.
So that's why you get underestimated variance. And a longer length scale because it effectively overestimates noise. It explains with this heteroscedastic noise rather than the underlying function.
Yeah. Yeah. Does that make sense?
Overestimating in that way that kind of underestimating dependencies.
Yes.
Yeah.
Yes. So it'd be less correlated than they should be.
For example, if you take a sum of marginals,
Mm-hmm.
sum of related values, variance for that is probably then overestimated.
That sounds plausible. Yeah.
That would be easy to check also. Funny that no one has done that.
We'll add that to the list. Convergence proof and the Aki conjecture. Okay. Let's plow on. Most of the technical stuff is now done. So if you have technical questions, this is as deep as it gets, basically. So we'll forge on. Here's one just minor tweak. All the tweaks from now on are minor. So here's a minor tweak to the EP algorithm. Let's, instead of removing one whole pseudo likelihood observation, let's just remove a fraction. So Tn raised to the power alpha. And let's not include a whole likelihood. Let's include the true likelihood raised to the power alpha. okay? And then carry out the projection step, the KL minimization in exactly the same way. And let's just be careful when we update. Remember that the tilted distribution just included p to the alpha here. So when we do this division, we need to make sure that we set t to the alpha equal to this discrepancy in here, because that was what we were trying to capture by that tn here. So we update tn to the alpha. And again, you can run this algorithm. This is called power EP, and it effectively changes the divergence that we're optimizing here. So the fixed points of this new algorithm, which is just as tractable as the old one, are equivalent to, instead of minimizing the KL divergence in here, minimizing a thing called the alpha divergence, where alpha is exactly the parameter over here. And the alpha divergence between P and Q, this relates to some of the things that Dustin was mentioning earlier. Different divergences for approximate inference. It looks like this. Okay, so that's equivalent to minimizing this. Can you read that? That's bad in green. Alpha divergence here. So this has the property that as alpha tends to 0, d alpha pq becomes equal to KL QP. And as alpha tends to 1, d alpha pq is equal to KL, exactly as we have below PQ. So if alpha is equal to 1, we get back this thing. And that makes sense if we stare at the algorithm. If we set alpha equal to 1 here, this is exactly the same as the EP algorithm to start with. And as I take alpha slowly to 0 in the limit, the KL divergences flips around, and we get the one that we used in the variational method with the Q to P rather than P to Q. So this gives us a way of interpolating between the two methods here, which is nice. Okay, happy with that? I forgot about that one technical bit when I said there was no technical bits left. Yeah.
So when do you decide to go from alpha? What would you do? How do you change alpha during the whole thing?
Oh no, you set it throughout. You say I'm going to do this alpha. You set that, and then you run the algorithm. Yeah, you don't. Well, you could anneal it as you go through, but I don't think I've looked at that. Yeah, we've never tried that. Interesting thing to try. Yeah. Yep. Yeah, outside of that, this becomes ill-defined. It's not a divergence anymore. Yep. Yeah. Any more questions about that? Okay, so now we've got this method which can do different things. So it turns out that if we know when alpha is equal to 1, we get Fitzy, which are these papers. But it turns out as we take alpha tends to 0, and we're using the variational KL, hey presto, we get back the variational method, the Titziat's method we talked about yesterday. So this is now a special case. These two things are special cases of this. That's not obvious, but it happens because local KL Q to P minimization, remember here we're looking at just the effect of one data point at a time. So although we're looking at the variational KL, it wasn't clear that that local variational KL was going to be the same as global KL minimization. But it turns out that for KL Q to P, local minimization is the same as global minimization. So you can run VI in a local way to get to the VI solution. So this is the general form of the fixed point for regression. I'm not expecting anyone to look at that really. The important thing is now we have sort of a unifying framework that can go from Michalis's method, the variational free energy method, to the Fitzy method, and can do anything intermediate between the two. So we can sort of do something that's halfway between Fitzy and variational free energy methods. Yep.
So if you can do each one of the KL divergences
Yep.
on their own, could you use that for doing like a stochastic variational thing where you optimize where you do the KL divergence for every single one at the same time and then combine them?
You could do, yeah. I think, well, in particular, I think the best thing one of the best applications of it is online stuff.
Yeah.
So you can now do nice online inference, which is really hard to do. In fact, this converts back to the streaming VI work of Tamara Broderick and stuff before that another Sato did and Zubin worked on. This is exactly online variational inference if you just make one pass through the data using these updates. Now what's nice is you can go back and revisit some data as well. So you can sort of blend the two approaches, which is good. I'll talk a little bit about that at the end. But you can do that for any intermediate case. In fact, Manfred's original paper was the online case. That's one reason why it wasn't spotted. It's not EP. EP wasn't invented back in 2002. So he was doing ADF, basically, which is one reason that people didn't spot the equivalence. Great. Here's two other generalizations. So one trivial thing to do is, rather than having single data points and using a T to approximate a single data point, we can group a bunch of them together into a little block. So pick little groups of disjoint groups of data points and approximate each group with a corresponding T, one for each group. And then you can run the EP updates as you would normally, now including a group of data points and approximating that group by an approximating factor. And that gives you this PITSI approximation that I think Ed came up with, and also the Bayesian committee machine. When we did this, we thought, oh, great, we'll be able to get the PITSI version of the variational free energy method. So we'll do exactly what Ed did and then take alpha to 0. And disappointingly, this recovers exactly the Titsy-Atz method again. And this is related to this local global view of VI. VI locally is the same as VI globally. So if we group together data points and run VI on them, that's going to be the same as the global solution. And then the last generalization we'll talk about here is we can also put the pseudo data in a different space. That's not something we've talked about so far, but imagine we invent a new process G, which is taken by taking our original process F and then carrying out a linear integral transformation. Okay, so imagine we take F and we pass it through this infinite dimensional matrix here to give us a G. This is just a linear combination of Gaussian process random variables. So this also is a Gaussian process on the left here. And if we pick tractable W's, i.e. ones we can integrate against the kernel of F, then we can compute the covariance of this guy and the cross covariance in the new space. And we can invent a new space in which to place our pseudo data and use that to induce dependencies on the original space F. And then we can optimize this transformation such that it generates a really informative embedding of F for putting pseudo data in that maximally explain a posterior in a parsimonious way by optimizing the inducing inputs. So this is quite a nice way of adding sort of extra flexibility to your approximation. And you can do the same thing here. In our case, it just means modifying the prior here to have F and G and using the TNs to approximate the likelihoods again. And it turns out it recovers these two papers. And I should also have Maurizio's paper in here, which predates this, in the two limits, alpha equals to 1, alpha equals to 0. These are called inter-domain transformations in the literature. Some nice papers on them. So here we go. So that's what we've done. To summarize everything we've walked through here, we have the literature has essentially been traversing these prisms for the last 15 years. So at the bottom here, we have the PITSI approximation, which is equivalent to EP. Over here, we have Michaelis-Titsy-Atz method, the variational free energy method. This is the regression case, and that's as alpha tends to 0. This is the structured approximations, where we group data points together that gave us the PITSI approximation that Ed worked on, which is also an instance of EP. And as we take the limit that alpha tends to 0, we go back to the variational free energy case. We can't get to this far part of the cube out here because variational free energy versions of PITSI get us back to VFE. That's why we get this sort of prism shape. And then the final sort of axis of dimension of the cube is the interdomain transformation up here that adds interdomains on. So the regression cube is fairly well populated. The classification one much less so. Various vertices have been figured out, but not all of them, and now we sort of populated this. These are all the references as well. Great. Okay, so that's sort of the cube that the field's been boinging around in the last 15 years. One question that you get at this point is how should you set the alpha parameter? And we don't really have a definitive answer for this, but here's some empirical evidence that maybe something in the middle is does fairly well on average. So we took 8 standard regression data sets, 20 random test training splits, and we varied the number of inducing points from 0 through to 200. We optimized everything, the hyperparameters and the inducing input locations, And here I'm plotting, and so we run, thousands of experiments here, aggregated all the results together, and first off we looked at how good the mean squared error from the predictions are, how close it was to the actual data points on the test data set, and we ranked where each setting of alpha, so 0, 0.2, 0.4 through to 1, how well it did on average. So 0 is the variational free energy method. That tended to come 5th on average out of, I think, the 8 methods. EP was the worst. It tends to come around 6th on average. And something in the middle tend to come 3rd on average. So around about an alpha as a half seem to do quite well on the mean squared error. Notice that the variational free energy is better than EP in terms of mean squared error as well. That typically tends to be the case. It always is a little bit better than EP in terms of mean squared error. For log loss, so log loss is just evaluating the probability of the held out data. So you have to get error bars correct to get good scores on this metric. In that instance, the variational one tends to be the worst. It was 7th on average, and EP tends to be better than it, but somewhere in between seems to do a little bit better, maybe on average as well. So there's a little bit of a dip in the middle. You see similar things for the classification data sets. Here we have error rate, and again the log loss. And again, EP seems to do quite well in this case, better than the VFE, and somewhere in the middle is a bit better, and similarly for the log loss. It's not clear cut, it's data set dependent, but these are sort of aggregate results. Aki.
You optimized, and what kind of priors, and why, and what would happen if you integrate?
I have no idea what happens if we integrate.
In a way, I kind of suspect that EP might work better
If you integrate.
integrate, and in a way now that but you're somehow able to regularize more by using different alpha, maybe.
It could. There are a huge number of factors at play here. So, yeah, it's entirely possible. There's like difficulties in the optimization.
Now when we were talking about this, the EP is underestimating the dependencies, and now it then also comes up to mind that maybe that's why slightly smaller alpha is good also, maybe. But now can't be convinced before I know the integrated result also.
All right, we'll do that one too. That could take a while. There's like 1,000 experiments for each one of these. So, great. Any other questions about this? Yep.
I have a question about the earlier stuff, the couple of slides back.
All right.
So is the doing it in this, so finding your U's in this transform space.
Yep.
Is that somehow equivalent to transforming your initial function into a new space?
Yes. I mean, we do transform the function. So, there really, it's like, I mean,
So the follow-up question.
whenever you define a Gaussian process, I could define possibly infinite set of other functions which are linear transformations of that original function, right? So one way of thinking about this is there is any possible linear integral transformation of my original function out there that's just defined as taking that function and integrating it against this infinite dimensional matrix here. And usually we don't care about those functions, but here we're going to put the inducing points in one of those functions so that they induce a posterior over the function I actually care about.
But you might care if you're doing, say, transforming to an alternative domain.
Yeah, yeah.
Where that is better starsification or something.
Yeah, exactly. And it relates to multitask, like this relates to multi-output GPs and multitask learning as well. This is one of the sort of common ways to induce dependencies between two functions, is to define one as an integral transformation of the other. So Neil's done work on this, like his latent force models relates to this. So. Great. Anyone else want to go backwards further? Okay. Right, last little bit. Let's just talk about how to do online inference. This relates to Alan's question. So this is how you can do streaming methods for Gaussian processes. So imagine you've got a whole stream of millions of data points that are coming in, and you want to update your posterior after you see each sort of new data point. And you don't want to have to go back and look at the million data points that have came in before. You just want to look at the previous posterior and convert that into your new posterior by integrating the current likelihood. So here's the idea. The new posterior is just the new likelihood times the old posterior. There's a slightly better thing you can do, which is to say that the new posterior is the new likelihood times an approximation to all the old likelihoods, because remember that the old posterior also includes the prior. Okay, so let's divide out the prior here and include the prior over here. And the reason why that's a good idea is we'll want to be doing online optimization of the hyperparameters at the same time. We'd like to maybe change our length scale as we see more data, or optimize our variance. And the prior parameters are all embedded in this old posterior, so we wouldn't have access to them. So let's divide out the old prior and put the new prior in here, and then optimize this for the kernel parameters at the same time as we see new data points. So that's a smart thing to do. And then the second thing is we can then write down this sort of Michaelis-Titiat style variational approximation here for Q of F. The dumb thing to do would be to use the same pseudo point locations throughout, but really we'd like them to move around. As more data comes in, we'd like to use inducing points in different regions of the space. So what we're going to do is our new approximation is going to use a possibly entirely new set of inducing points, and they could be completely different from the old ones as well. So this will allow the inducing points to move around over time. We can optimize those. In this context, variational free energy methods are much better than any of the other Parry-P methods. Much better than EP at least. So here's an example of this in action. Imagine we've seen this chunk of data, we fitted our squared exponential GP, and then some more data comes in. And we use the online method just to update to fit the new data. And the online method hasn't gone back and seen these data, it's just seen the blue thing above, just seen the posterior. And notice how it's used all of the inducing points here across the observed data, as it should do. But as this new data's come in, it's now spread the inducing points throughout the data. It's moving them along all the time, and it's changing its hyperparameter estimates, and here's the final batch of data coming in. It's spread them out even further to cover the new data points. And this is the batch solution. If it's seen all the data at once, what would have the variational free energy method done? Well, it's a bit different. This one's a bit more overconfident, but it's still not a bad estimate for the posterior in this online way. And here's another example from classification, a two-class classification problem where you see this data batch to start with, then you see this other region of input space come in, and then finally you see this other region of input space, and these are the learned class boundaries, and they look pretty close to the ones you'd get by running the batch version of the algorithm. And the black dots are the inducing inputs, so they've moved around to cover the whole space by the end. The error rates are roughly the same in the batch case and the online case. So there's a really nice framework now for doing online VI. Okay, I'll skip that. So here's a summary. We've provided this sort of unifying view which brings together Michaelis-Titiats's method, the variational free energy method, the FITSI method, and provided a continuum of methods in between that look a little bit better than both of them in some average sense, admittedly not integrating out hyperparameters. FITSI is the EP in disguise, and PITSI is too, which sort of resolves these philosophical issues that we were having yesterday. I was very troubled until I discovered this. And VFE seems to be the best in the online setting. These are the two papers that cover most of this stuff, but happy to take any questions if you got them too. Yep. Oh, just one clap. I think that's it.
In the online method, if like new data is coming in long enough, is there a point where you're going to actually have to add more inducing?
Indeed. Remember the plot yesterday of the time series?
Yeah.
We needed as many inducing points as there were wiggles in our function. So at some point, we're going to run out of capacity.
Is there a good way to determine that? Like,
Yeah, I think you can look at the residual. So remember the variational free energy has a thing which looks like the average reconstruction cost as its first term. And so if that average reconstruction cost starts to wing up, it gets bigger and bigger and bigger, you know you've run out of inducing points. So there are definitely tractable metrics to compute when you need to add more inducing points in.
but then like on the updates, can you still use that trick where you're using?
Yes. Yes. So the new points here can expand in size.
Okay.
So this could be It's this can be an arbitrary number of new inducing points. Yeah. All that's happening is the KL is before you do the KL divergence between the prior and the likelihoods and the Q distribution. Maybe I should have said the other way around, the new Q distribution and the prior times the likelihoods. You just substitute this in for the prior in that update. So it doesn't matter, it doesn't really affect anything. Yeah. Andres?
In the streaming, again, if I can go back to the figure. So for example, in the third line,
Yep.
if you were to give to a GP all this data and let it converge, would the fit look similar?
That's this one.
That's from the beginning.
Sorry?
That's if you give everything.
This is batch, yeah. This is the normal batch mode.
Okay. Because so if you give everything, not like one batch, all the data in one batch, and let it converge, is this?
That's this, yeah. This is the batch solution. So it is, notice the error bars are a bit fatter. So VI, we know, is often underestimates the error bars a little bit. And when you do VI lots of times, that error will compound, I think. So the uncertainties here are just a little bit smaller. Not everywhere. Maybe here it's a bit bigger, actually. But like here, it's definitely smaller. Here, it's probably a bit smaller.
What about the location of the inducing points? Can you argue or prove anything about how, if for example, you do the online, maybe like first it seems to go maybe to the new batch every time, or can you?
Well, that's the interesting thing. It doesn't do that, right? I mean, they were all here. It left a bunch of them behind, but it probably left as many. It used 1, 2, 3, 4, 5, and there are 5 here. Maybe there are a few fewer here. It's pretty good. I mean, it is really pushing.
Can you prove anything or
I wish we could. Yeah, I don't think we can. I don't think it's very hard to prove the relationship between the two. We can if we don't move the pseudo points around. So for regression, if you do the online thing and you don't optimize hyperparameters and you don't optimize pseudo points, it will give you the exact solution after you've made one pass through. If you're optimizing the pseudo points and the hyperparameters, then all bets are off. Yeah. Great. Right. Thanks very much.